Welcome back, statisticians. We are going to take a look today at how to do normal approximations to the binomial distribution. In a second video, I will talk about how to do this with the p-hat distribution. Knowing how to do it with the binomial distribution is going to be more important for you, however. The other is important too, but just not as important. So what are we going to be able to do over this video and the next? We're going to be able to talk about what assumptions we need to be able to use to do this. We're going to be able to compute mu and sigma for the normal approximation. We're going to use the continuity correction to how we're going to enter these things. We're going to potentially be able to convert x scores to z scores. We don't actually have to do this for what we're doing. We don't need that to be up on the calculator either. So we're going to be able to do if we had to, though. And then in the next video, we'll talk about p-hat specifically. So let's talk about vaccines. That is currently relevant. This particular case is a new vaccine for cholera. The probability that this new vaccine will protect adults from cholera is known to be 0.85. The vaccine is administered to 300 adults who have to enter an area where cholera is prevalent. What is the probability that more than 280 of these adults will be protected from cholera by the vaccine? This is a type of binomial experiment. We have 300 trials, that's our n. Our probability of success is 0.85, and the number of successes r, or x in the calculator, we want to be greater than 280. So 281 through 300. Now, we could use the formula for the binomial distribution, but that would take a long time. It would even take some time on the calculator. So there's an easier way to do it. Under certain conditions, we can approximate the binomial distribution with the normal distribution. Those conditions are this. If n times p is greater than 5, so the number of trials times the probability of success on a single trial, if that is bigger than 5, and has to be both, not either or, both, n times q also is bigger than 5, then we could approximate it. We're going to have, again, some special formulas for mu and sigma here. So mu in this case is n times p, and sigma is the square root of n times p times q. So one thing we could do is we could graph a binomial distribution. So here is one where p is 0.25, q is 0.75. The number of trials, the first time we have 3 trials, then we have 10 trials, then we have 25 trials, finally we have 50 trials. So using a computer program, your authors got this particular graph for these things. You are not going to have to do these binomial distribution graphs by hand. You should be able to interpret them if you see them. So in this example, for example, so we have 3 trials here where n is 3. The probability of 0 successes looks to be a little over 40%. Probability for 1 success is a little bit over 40%. 2 successes is just under 15%, and all 3 successes looks to be about maybe 1% thereabouts, maybe a little more. If we had instead 10 trials, we see that the probability of 0 successes is about, I think they have the wrong thing there on the y-axis. This should be 0.05, I believe. So that's about 5%. 1 is here, 2 is here, 3, 4, 5, 6, 7, and more. If we have 25 successes, we see our probability graph here. If we have 50, we see our probability graph here. So n times p here, greater than 5. N times q is greater than 5. So we are, we're good to go for these larger values. I should say for some of these larger values. For this one, we have 50 times 0.25. So as we get bigger, notice how we get closer and closer to our normal curve. That's what we're looking for. Now, one thing you're going to have to do here is what's called making a continuity correction. Because x is a continuous variable, and what we're going to work with are discrete variables. So to do this, we are going to do one of two things. When x is the left point of an interval, in other words, when it's the lower number, we're going to subtract 0.5. If it is the right point, we are going to add 0.5. And you'll see that on some of the sample problems that I've done in another video, and we'll also see it on a sample problem we're going to do in this video. So the sample problem we're going to do, in fact, is going to be, we're going to go back to our original problem. We're going to figure it out that we had at the chapter start. So this was our problem. We have a new vaccine. It's probability probability of success is 0.85. We want to know what is the probability that more than 280 will be protected from cholera by the vaccine. And again, we have some things we have to be aware of. We have to be aware that mu is going to be n times p, and sigma is the square root of n times p times q. To do this, so we're using the normal approximation, so we're going to go to second key in distribution. We're going to choose normal CDF. Our lower value here, we want more than 280. So our lower value is going to be 281, that's more than 280, minus 0.5. Remember, we always subtract 0.5 from the lower value. You could do this yourself. You could just put 280.5, but the calculator will do it for you. For the upper value, we could just put 300 because that's the total number of the population. I'm going to just put a bunch of 9s here because that's what we often do with normal CDF. So mu, again, mu is n times p. N is 300. P is 0.85. And then sigma is the square root of n times p times q. Remember, q is always going to be 1 minus p. So if p is 0.85, q is going to be 0.15. So there is, if I did everything correctly here, a very low probability that more than 280 of these adults will be protected by from cholera by the vaccine. We have 0.0002 approximately. So that would not maybe be the best vaccine to use in this situation. So again, we have a case where we might have a very much a real world situation being used where probability is used. So the next video, you're going to learn about the p-hat distribution. And then again, there's a video where I've done one example of a problem like this. If you have questions, please let me know. Good luck moving forward.